Hello students, welcome back. Let us resume our discussion in section 3. We only have one more problem left, and this one is the hardest of the bunch. Determine the intervals of increase and decrease of the given function. Now, in order to determine the intervals of increase and decrease, we have to take the derivative and factor it, so that we get all those critical numbers in the number line, and then determine when the derivative is positive, so that the original function is increasing, and when the derivative is negative, so that the original function is decreasing. From that diagram, I can get the increasing, decreasing intervals. That's, of course, a difficult method, and a little bit easier method is to plot. Let's plot this. And then x is running from -5 to +5. I don't know. Is this appropriate? It's hard to tell. And okay, let's mathematical run. Well, while Mathematica is working hard, let's go ahead and we can use our brain to figure out a little better solution. Let's take the derivative of the given function. The derivative of this function given by the integral. So we're just plugging in and then plugging in x squared plus 1 in place of this y. And then another y here, so x squared plus 1 here. And then we have to multiply the derivative of the inside. And then by now, I hope everybody can easily figure out the other term is going to be 0 because we have a constant. Just plug it in and take the derivative of 1. Derivative of constant is 0, so that's 0. We have this kind of graph here, and we have some wiggle here. Let's zoom it a bit closer. Yeah, we have some W-shaped forming here. Okay, where were we? All right. Let's mathematical run, and let's go ahead with the derivative computation. And then, if you set it equal to 0, you'll be able to find all critical points. But let's see, we have a denominator here. If you set this one equal to 0, denominator doesn't do anything. So we can go ahead and rewrite into factored form like this. And then this one here, x squared plus 1 plus 2, x squared plus 1 minus 2 minus 2, and then divided by this denominator. Maybe a little bit bigger font will be helpful. So, okay, all right. Here's a graph. Apparently decreasing its local minimum, increasing its local maximum, decreasing its local minimum, and going back up. That's what I expect. Okay, let's come back. Let's take the derivative, plug in the top and the derivative, and then we just took the common denominator here, but let me try to explain what I did here. In the numerator here, do you see square minus 4? Basically, in the numerator, a squared minus 2 squared can be rewritten as a plus 2, a minus 2, like that. That's what I did here. Does it make sense? Squared minus square, so x plus 1 minus 2, x plus 1 2 plus 2, and then this 2x, which I just highlighted in blue, stays here. Okay, let's simplify this further. Copy and paste this thing, and then we don't need all those colors anymore. Oh, come on. X squared plus 1 plus 2, so plus 3. X squared plus 1 minus 2, so minus 1. We can rewrite like this. And now please note that x squared plus 1 is all set. This is irreducible. Always positive. So we can work on x squared minus 1. So that's, this thing is going to become x plus 1, x minus 1, and then we had x squared plus 3 here. Okay, all right. And then let's highlight this one in green. Let's highlight this one in brown. Okay. The derivative computation is done. We took the derivative computation here. Then afterward, it's a factorization. We want to set it equal to 0, so we have to factor it, and then we did some factorization here. And I could have just broken up a part and then refactor, but that's going to be probably too hard. So a little bit clever method is to regard a squared minus 2 squared, so separate like this, as highlighted in red. And then did the computation, we get x squared plus 3, that's irreducible, so no problem. The other x squared minus 1, that can be factored further, x plus 1, x minus 1. And as you can see, here, 2x gives me x equal to 0 right here. X plus 1 gives me x equal to negative 1 right here. X equals to 1 from there, from these three factors. In short, in terms of color coding, we are going to get these critical points. So this one here, coming from blue factor, and then this one here is coming from the green factor, and then let's see. Can I get brownish something here? Okay, that's coming from the brown factor, x minus 1. You can clearly see those. Now, as for when does this function increases or decreases, you can set up a diagram like this. So that's negative 1 right here, and then x equal to 0 right here, and then brown factor, positive 1 here, and then as far as the behavior of f prime is concerned, let's see, when x is really, really big, plug in something really big like 100. Everything is positive, all positives. F prime has to be positive here. And this one has odd multiplicity. You see we have power 1. So as I cross, I have to change the sign. Another odd multiplicity, change the sign. Another odd multiplicity, I have to change this. Should be negative. So the original function should be decreasing, increasing, decreasing, and back to increasing. And that's precisely what you're looking at in this graph. This completes the answer. Let's see, what did I do in my answer key here? Take the derivative and then minus 0 because this one is constant. And then, here I broke apart and then refactored. I did hard way. Here in my solution here, I looked at square minus 2 squares, so x squared plus 1 plus 2, x squared plus 1 minus 2, so we got the irreducible and x squared minus 1 a little bit easily. But here in my answer key, I wasn't clever enough to see that, so I just broke apart everything and refactored. In the end, I got the same thing, 2x blue and x plus 1 green, and then x minus 1 brown. So x equals to negative 1, x equals to 0, and x equals to 1. Those are critical numbers, x coordinate of the critical points. And then they all have multiplicity 1, so we have sign change on both sides. So you can do the sign analysis like this. Plug in big number, like infinity, so all positive. That's the easiest place. And then keep crossing those critical numbers. They all have odd multiplicities. We have the sign change, minus, plus, minus, so that decreasing, increasing, decreasing, increasing, and that's visualized by this graph here. Okay, so we can combine all those things that we did earlier with the derivative computation of functions defined by definite integrals. Whenever something like this shows up, expect something really hard. Well, what can I say? That's the nature of the definite integral, and that's why these things are called the fundamental theorem of calculus.